Okay, so here we have these extra problem solving questions for the Unit 3. Some of them also go a little bit into the higher level section. I'll try and mention those as I go along. Okay, so I'm going to do the multiple choice first. So the Kelvin temperature of an object. So Kelvin temperature of an object is a measure of, now this is straight from your definition, the average kinetic energy of the molecules of the object. It's not the total energy because that would be all the kinetic energies added up. So this is the only one that is directly applicable. Okay, going to 2, we have two identical boxes X and Y, each contain an ideal gas. What do they mean by identical box? What is meant by identical boxes? Well, that means that the volume in each case is going to remain the same. So we're looking at the ratio of px to py. We are told that there are n moles here. There's n moles, the temperature is T and the pressure is px. And here you've got 2n moles, the temperature is T over 3 and your pressure is py. And you're looking at that ratio. Now obviously we're going to use our formula PV is equal to nRT. And we're going to divide through by V. So I've got that. So if I've got px, if I'm looking at x, there would be n moles there. R is your constant and T is your temperature, and the volume x, the volume is going to be staying the same. And we're dividing it by py. So we're going to divide by py. That's going to be n again, but there are 2n, so it's divided by 2n. Times by R times by T over 3, and also divide by Vx. So then we invert and times, so we're going to have nRT over Vx times Vx or Vy, that's exactly the same, over 2nR T over 3. Here we see that our R will cancel this R, that R will cancel that R, that N will cancel that N, that Vx will cancel that Vx, that T will cancel with T. And here we're going to be left with 1 over 2 over 3. So when we divide that, that will be 3 over 2. So B would be your correct answer in that case. Okay, so moving down to questions 3 and 4. We have in 3, the specific latent heat of fusion of a substance is defined as the amount of thermal energy required to change the phase of. Now, this B would be the correct one because it is for unit mass, and because they're talking about fusion, we're talking about a substance to a liquid at a constant temperature. Okay, so fusion is always talking about a solid liquid change. Going on to question 4, it says a fixed mass of an ideal gas is heated at constant volume, so the volume remains the same. Which one of the following graphs best show the variation with Celsius temperature T with pressure P? Now we know that for a constant volume, pressure is proportional to temperature, or pressure is equal to K over T. But this T over here is in your Kelvin scale. So if I had a graph like that for Kelvin scale, I would have my T there and my pressure there, and you would have something like that. But because this is not Kelvin scale, but your Celsius scale, we're actually looking at the graph somewhere over here where this is 273 Kelvin, 0 degrees Celsius. So we have that situation that we're looking at. So we'd be looking at A, would be our correct answer there. Going on to question number 5 and 6. Okay, so we've got the distance between 0 and 100 degrees marked on a mercury in glass thermometer is 20 20 centimeters. So from 0 to 100 is 20 centimeters. When the thermometer bowl is placed in a mixture of ice and salt, the mercury level is 4 centimeters below 0 degrees Celsius. Mark the temperature of the mixture is. So basically you're going from 0 degrees to 100 degrees Celsius, and you've got 20 centimeters. So each 1 centimeter must correspond to 5 degrees Celsius. So if we're 4 centimeters below, that would correspond to 20 degrees Celsius. But because you're below, you're going to be minus 20 degrees. Next one. Some liquid is contained in a shallow dish that is opened to the atmosphere. The rate of evaporation of the liquid does not depend on. Well, it definitely depends on the temperature of the liquid. The temperature of the atmosphere, it would have an effect to some degree. The depth of the liquid, no, because this is a surface phenomena, and the pressure of the would have some effect. So this would be looking at C. All right, going on to question 7. We have in this one, in question 7, we've got the equation of state for an ideal gas is PV is equal to nRT, describes the behavior of real gases. Okay, so this describes the behavior of real gases. Now, it would describe the behavior of an ideal gas for all pressures and volumes. Now, for this one over here, I would probably say it is A, only at low pressures and large volumes. It's at high temperatures, only at high temperatures also is a possibility, only at large volumes and large pressures. Not at large pressures isn't good because you're forcing the molecules close together. So it's between those two. And, well, I'm not quite sure which one I would go for there. I'd have to do some more thinking about that. But one of those two. Very high temperatures, it depends what they're talking about. Perhaps the best one would be, that one would be B. But certainly A also. Very high pressures would cause a problem also. Okay, going on to question 8. The temperature of an ideal gas is reduced. Which one of the following statements is true? Here we have the molecules collide with the walls of the container less frequently. That is true because the velocity decreases because of the lowering of the temperature. That's the measure of the average kinetic energy. Kinetic energy is a half mv squared, so the velocity is going to decrease. That would be the best answer here. The molecules collide with others more frequently. No. The time contact between the molecules and the walls reduces. A perfectly elastic collision, so that probably wouldn't change all that much. And the time in contact between the molecules is increased. Also not major. So we are looking at A. Looking at 9, a temperature scale is constructed using property X of a substance. Which of the following must be characteristic of property X? Now I would think that D would probably be the best answer. The value of the property must vary linearly with Kelvin temperature. So you've got something like this. So you've got X and you've got your temperature. So if it's varying linearly, something like that, then for each X there is a value for T. So there's only one value of X or one value of T. So that basically describes that. But also because it's linear, there's a linear function between them. So you could have something like X is equal to MT plus C. You would have some linear function. So as soon as you knew the value of X, you could work out your T from that. So I think D would be your correct answer there. D would be a good answer there. Okay, going on to question 10. and 11. Thermal energy may be transferred. This fluid is a result of density change. This is convection. This is when you get currents that move the heat, and this over here is conduction. Conduction. It's not actually part of the curriculum, this, but it would be C. It would be convection and conduction. Going on to question 11. Which of the following is not an assumption on which the kinetic model of an ideal gas is based? And it's B. All the others. Perfectly elastic spheres. The forces between them are negligible unless they're in contact. Continuous random motion. All of those are correct. Only B is not one that we use. And then the last question of the multiple choice. 12 here. We have, as part of an experiment to determine the latent heat of vaporization of water, the student boils some water in a beaker using an electric heater as shown. Now the student notes two sources of error. Thermal energy is lost from the sides of the beaker, and as the water is boiling, water splashes out. So, if thermal energy is lost, we are assuming that all the energy when we're doing this, all the Q that's coming out there is going into ml. So, if we have to add more of that, if we have to add more than we need, then L obviously would also be more. But if you've got less of this, if water is coming out, so this becomes less than there actually is because you lose some, then again your latent heat is going to be divided by something smaller, so this L is going to equal Q divided by M, and if this becomes less because it's splashing out, L will also increase. It will tend to cause it to increase. So there's no answer for this that I'm getting. If there is less, let me just check this again. If there is less mass, and so you're going to, yeah, I would say at the moment, I'll get back to you on this, but I would say that both of these are going to lead to an increase